Hello everyone, it's Musa Joseph, machine learning enthusiast, researcher, and a student at Makerere University, presenting to you a project titled as follows. This project aims at solving problems originating from the fact that Uganda's Tier 4 finance institutions operate outside formal credit bureaus, lack formal regulations, and have no formal credit history, and therefore have no data-driven decision support system to assist them during loan decision making, and therefore they operate at high portfolio at risk. When we talk about loan application gatekeeper, this is our module that gives risk score for every loan application. Loan monitor, this is the module that gives early warning for loans which are becoming stressed. XGBoost is simply a machine learning model architecture. Sharp is a mechanism that we use to generate explanations that our models for the predictions that our models make. And then area under precision recall is a metric that we use given our class imbalance problem. And then group shuffle split, this is a mechanism that we use to overcome data leakage that occur when data from one institution gets into different partitions of the train, test, and validation. Various works that have been done, some of them are listed here, starting with the first one, which uses logistic regression. This one requires linear data only available in formal credit history. The second one here carries no group shuffle split, has leakage, and does not generalize well. A problem we solve through implementing group shuffle split. And the third one has no informal sector features such as is school fees. And we resolve that problem by involving several informal sector features. And this one here has no sharp explainability required by the regulations, and we resolve that by implementing Sharp for the explanations. Our own model, we implement and evaluate over 8 models and then select the best model based on stability run, and then adversary area under curve of 0.98. This one there justifies our use of group shuffle split. And our main limitation is that we are still operating in a single country based on the data that we use belongs only to Uganda. And the problem here is that most of our circles, the loan officers grant loan based on their failings, the relationships, and some repayment narratives. And they only get shocked when the loans are defaulted without any prior warning. The collaterals have disappeared. And then they also have problems in identifying if borrowers have defaulted in other institutions before coming to borrow from them. Computation problems, we have class imbalance, whereby in our data set, majority of the cases are non-defaulters, higher than the default cases. Therefore, it needs a careful design. Otherwise, a model will give you 75% accuracy while performing no prediction at all. Institutional leakage, I talked about it, whereby data whereby data from one institution goes into different partitions of the train, test, and validation. She's not seeing. And then you looking at we aimed at carrying out exploratory data analysis and then designing, training, comparing 8 models, and finally selecting the best. And also we wanted to deploy these APIs to be available for use. And then in our question, we wanted to know which features carried the most predictive signals. And then we wanted to know which ML architecture is the best for our kind of problem. And we are also asking ourselves, how can we use CHAP to ensure explanation for the predictions that our model make in order to meet regulatory requirements. And then in achievement of these objectives rolled in straight as our contributions, where we successfully carried out the exploratory data analysis revealing key insights such as over-collateralization paradox. And also we successfully trained and evaluated, compared, and selected the best model under leakage hardened protocol. And then we also deployed this model in production, MV product for use. And here is our simple system architecture. At a very high level, we have the local, where the brain of our system is built and then moved to the cloud, where it interacts with the problem owners here. And then starting is where our brain is built. We started with data ingestion, we progressed to exploratory data analysis, which gave us modeling decision that we effected in feature engineering to produce features that are ready for model training. And in our model training phase, we implemented a science kit pipeline to ensure that all the data goes through a same pre-processing pipeline, whereby we used median imputer to fill in the missing values for numerical columns, and then robust scalar was prioritized over standard scalar because of the outliers that our EDA revealed. Then we did one hot coding to generate binary columns for categorical features, because this XGBoost clarifier mainly understands the binary columns, not the strings. And then we did 7 steps leakage audit, the leakage auditing, to ensure that our model is actually accurate but not cheating, looking at the future. And then we did the model evaluation and comparison, and then selected the best model based on stability run. And then we compressed the complex very wise model into a simpler but yet with the same knowledge into and then we deployed this model. Here basically you can look at the request coming to the API endpoints, and then API sending it to the model here, and then the model makes the prediction, logs to the database, gives it also to the API, to the database mainly for performance monitoring and then future improvements of the models. And then our dataset comprises of over 19,000 train eligible records with these categories of variables. And then all the personal identifiable information, we hashed them cleanly. And then we had to feature engineer our target variable using strict logical conditions. And but still we realized the class imbalance of 3.1 to 1, and which is clearly revealed by our visualization here, whereby if you look at the fully paid loans, they completely outweigh all the conditions that make up the default, that is the class imbalance case. And then here we look at it, and although it is not clearly a monotonic relationship, but we can look at it, there is a clear linear relationship here, whereby as the loan duration increases, the default rate also increases significantly. And we also look at we also have We also have the school fees seasonal effect, whereby you look at it in January, whereby the loan counts increases and default rate also increases. This gives us a clear modeling decision of putting a school fees mass in our feature engineering. So looking at the model one by one, starting with XGBoost mainly, I said that XGBoost is mainly ML model architecture, which builds its tree incrementally, and each tree aims at refining the prediction or decision made by the previous tree. This model does not only aim at being accurate, but also aims at being efficient and simple. That's why it's made of the objective function, which is the main goal, comprising of the loss training loss function and the regulation function. And then regularization function is comprised of the gamma and lambda parameters, which acts as penalties for any extra tree that is made. The tree is built incrementally, and this one here stands for the decisions that is made by all previous trees, and then this is the decision by the current tree, which is standardized by the learning rate to ensure that the model learns slowly but robustically. And then we resolve the class imbalance root scale pose weight, whereby this 12,000 here stands for the non-defaulters and 3,000 stands for the defaulters, giving us 3.26, which implies that we need to penalize misclassification of non-defaults, misclassification of defaults 3 times more than when we misclassify a default. So looking at decision tree as a model, this one is just a simpler model that we generate after distillation, and it mainly learns from the teacher's soft labels. And when we look at another model, which is a logistic regression, our ancient but yet powerful model, this model works by computing the weighted sum of all feature inputs plus bias, and then it passes it via a sigmoid function, 1 plus e to e exponent negative z. Mainly this to generate the final score, that is where it passes it. Mainly this function learns by minimizing the log loss on the training data, So that's how this model lands. And then we're looking at a random forest, the parallel community of trees. Mainly, this model trains a specified number of decision trees on a on a bootstrap sample of data, and then on a bootstrap sample of data. So to say that each of the tree will learn on a random set of features, and then the model averages their probability predictions. And generally, the final prediction is given by the summation of the prediction of all the models divided by the number. Then CatGBoost, this model mainly handles high cardinality categorical features using ordered target encoding, whereby whereby the encoded value of a borrower is given by the average of the labels of all the borrowers who came on earlier. So, and it does it in a random permutation. So, in that way, it avoids the target leakage. So, like GBM, this one is the a module which grows its tree leaf-wise by continuing to split the leaf that has the highest gradient gains, and it uses a gradient-based one side sampling in order to maintain all the high error examples, while randomly down sampling the low error examples or the simple examples. With this, it manages to be very efficient and fast. And then explainable boosting machine. This model for it is a generalized addictive model with pairwise interactions, and basically this with pairwise interaction, basically this model learns the separate smooth functions for each feature and the selected pairs of features. And then what it does is it it adds them together with a global intercept, and then passes them over a sigmoid link to generate the final score. So is that a user is able, or someone is able to draw a graph for each feature and generate explanation for why the model is saying whatever it's saying. Then tabnet, this model here selects a specific a specific subset of features to concentrate on for every specific kind of for every specific borrower. And how does it achieve it? It achieves this through its sequential attention mechanism using the Sparmax attention. That's what I can say about tablet. And then tab transformer, this one for it maps categories to less embeddings, and then makes each category to look at the categories to look at look at other categories in the same row, and then update its value in relation to those categories. So to look at our output results, and then we did circle this joint split to avoid the leakage that we talked about, institutional leakage we talked about later. So and then when we did validation in order to do hyperparameter tuning and then threshold determination, because we cannot set our rules basing on the final exams. So, but when focused on the tests here, we had various metrics to help us carry out evaluation. And then when we look at the bra, here is a metric which helps us determine how well our model is predicting probability in relation to the final outcome of 0 and 1. So we look at here, some models are really struggling, the likes of tabnet transformer, it's having 0.21, which is approximate to the base bra if we use a specific formula to calculate base using this default rate, which is the base rate of 30.14, we get also 0.1, which is the base bra. And if a model is getting a base bra, it's performing. But area under precision recall metrics helps us to determine how well a model performs under all possible thresholds. And here we look at it like, if we use an example of 0.63, we look at our model performing two times better than just a random model, a base model at all thresholds. And then in a rock area under curve helps us to determine how well a model distinguishes between a default and a non-default. So we look at 0.767. That implies that by 0.76%, our model will give high score to a defaulter than a non-defaulter. So it differentiates very well. So as I said that we did our selection on stability run, whereby we did 6 seed stability run, and then we got the average of the 6 results, and then the average of the standard deviation, the model with the least standard deviation in the metrics that matter most, as F2 score was one of our key metrics because it weights the recall greater than precision because it is better to cache all the defaulters than missing one non-default. So the best with least standard deviation and F2 score becomes the best model. And then we did explain AI results. We're using kernel explainer with link identity, whereby we used 200 samples of background data to act as reference for the sharp values calculations. And then we also produced these artifacts based on 500 test data, whereby this graph here, horizontal bar graph, shows us the average effect that a given feature has over across all predictions. And then this B swarm here shows us that the dots are the predictions, but then the red shows that the feature had a negative impact, and then the blue shows that the feature has a positive impact. Basically, it's showing the impact that the feature has on every kind of prediction. Now, this one is showing us waterfall curves, so seeing the defaulted case. This one positive impact, red negative impact, and then the defaulted case only blue. And then when we look at, we did model compression basically to just generate a simpler version of the complex model that we generated for performance purposes. And we preferred knowledge distillation because it helps us to preserve the logic, and also while building just a distinct model, a new model, like we built decision tree, a very simple one, yet retaining all the logic. And so how does the logic get retained? Through the dark knowledge mathematics here, whereby T is the temperature. As we increase T here, so the relationship between the two, the default and non-default, is revealed higher. So we reveal the teacher's confidence, and then here we strip the sigmoid compression to retrieve the teacher's zero decision. And then here we create the expert advice. So progressing, looking at our pipeline, we did the same pre-processing pipeline as the one for the teacher to ensure that the student whose data also passes through the same pre-processing, then establish the teacher's baseline, which we shall use to compare what we are losing in what we are trading off in order to get this efficient and fast model. And then we generate the soft labels. When we generate the soft labels of the teacher's confidence, then what we do is we again stuffed, and then we reveal the relationship, and then afterwards we sub to the student here. We do the loss blending, whereby we don't want the student to just cram. We tell you to learn alpha% from the teacher, but then 1 minus alpha% from the real actual situation. Then the next thing we did was to train the student, evaluate them basing on their baselines and the teacher's baseline. So this is the evaluation result. And then what we look at mainly, there is the teacher's baseline, and then their own normal baselines, and then their trained results. And then the model with the highest gain, that is the model we select as the best model. And then our model had 121% performance irritation. Is not about leakage or misengineering, but these are well-documented situation. In case knowledge distillation acts as visualization, preventing models from creating excessively complex noise-making trees and the logics. And then also when the models learn, the new model learn from the smooth labels that has been created by the teacher, not the hard ragged zeros and ones, rather the smoothened probability. And then we look at, we selected our model, the XGBoost, then distilled it, and then deployed it to production. These are the endpoints we produce. We are still in phase 1, whereby the model makes the decisions. We log them as we monitor the performance, but no decision is altered. And then this is our product demonstration. We demonstrate our product here. That is the interface. And then the limitations that we are having, mainly we have issues in data quality, and then also we never considered some macroeconomic thing situations such as inflations, and then our model may really perform somehow not well on in some geographical regions and economical situations. We don't guarantee that. And then also we assume that the records are kept digitally, but manual ledger environments may give significant performance and data integrity issues. So in conclusion, so we say this is the first circle destroyed leakage audited ML framework in Uganda, and our EDA revealed the key insights, which looked like the school fees effect, how they have impact in Uganda. And then other phases, we are going to look at collecting more data so that we can do more tab transformer stability analysis, then also